Hey everyone, and welcome back. Today, we're diving headfirst into one of the most mind-bending questions in all of cosmology. It's a question that pops up constantly when we talk about the cosmos. The question is simple to ask, but incredibly profound. If the universe is expanding, what in the world is it expanding into? It's a question that immediately sparks our deepest curiosity about the very nature of existence itself. Where does everything end? What's beyond that? This query really delves into the limits of our current understanding of space, time, and reality. It pushes the boundaries of what our brains are wired to comprehend based on our everyday experiences. It challenges our intuitive grasp of space and time, which is usually based on moving through a fixed background. But the universe's expansion isn't like that at all. So, let's be clear right from the start. The answer is definitely not simple. It's not something you can easily picture with everyday analogies, though we'll try a few. And perhaps the most crucial point to grasp up front is this. It's not expanding into a pre-existing outside or empty space waiting for it. That's the common misconception we need to tackle. To understand the expansion, we first need to touch upon the prevailing scientific model for the universe's origin and evolution. That model is, of course, the Big Bang theory. Now, the Big Bang describes the universe originating from an incredibly hot, incredibly dense state. This was the state of everything we can observe today, packed into a tiny volume. But here's the critical distinction, and it's a big one. This origin was not an explosion in space, like a bomb going off in an empty room. That's another common and misleading image. Instead, the Big Bang was an expansion of space itself. Space didn't exist beforehand for something to explode into. Space, time, and matter all came into being together in this event. Think of it as the moment the fabric of space-time began to stretch and grow. It wasn't matter flying outwards through a void. It was the void itself appearing and expanding. This initial rapid expansion, sometimes called inflation, set the stage for the universe we see today. It's the starting point for the ongoing expansion we observe. So the Big Bang wasn't an event within space, but the beginning of space. This is fundamental to understanding what the expansion means today. It's a subtle but crucial difference that helps us move away from the idea of the universe expanding into something else. Okay, so if it's not expanding into something, how do we even picture this? This is where analogies can be helpful as long as we remember their limitations. A classic and very useful analogy is a balloon with dots drawn on its surface. Imagine these dots represent galaxies. As you inflate the balloon, the surface area expands. What happens to the dots? They move further apart from each other. Crucially, the dots themselves are not moving across the surface towards some edge. They remain fixed on the surface. Their distance increases because the surface itself is stretching. Similarly, galaxies in the universe are moving further apart. We observe this through redshift, which we'll discuss later. But they aren't traveling through some pre-existing static space. It's not like ships sailing away from a central point in an ocean. This means that from the perspective of any galaxy, all other distant galaxies appear to be made from a central moving away from it. There's no single center point that everything is expanding from. Just like on the balloon surface, every dot sees every other dot moving away as the surface expands. There's no special dot in the middle. This is a key aspect of the expansion. It's happening everywhere at once, affecting the distances between unbound objects. So, let's directly address the big question again, armed with this understanding of the Big Bang and the nature of the expansion. What is the universe expanding into? The answer, from the perspective of modern cosmology, is that it's not expanding into anything in the traditional sense that we usually think of into. The expansion is an intrinsic property of space itself. It's not space moving through something else, it is the stretching of space. There's no pre-existing void or empty arena outside the universe waiting to be filled. The universe is everything there is, including space and time. There is no pre-existing container that the universe is growing within. The universe isn't a balloon inflating inside a box, it is the balloon surface itself. The expansion is a continuous stretching of the fabric of space-time. Imagine the grid of space-time coordinates getting larger everywhere simultaneously. As this fabric stretches, the distances between objects that are not gravitationally bound together increase over time. Galaxies within clusters stay together, but the clusters move apart. This stretching means the universe is becoming larger. The total volume of space is increasing. But this increase in size isn't happening by pushing into something external. It's happening because the internal metric of space is changing, making distances bigger. It's a bit like asking what the surface of the balloon is expanding into. It's not expanding into the air around the balloon. The surface itself is just getting bigger. The universe's expansion is the creation of more space, not the occupation of existing non-space. Okay, let's be honest. This concept is incredibly difficult to visualize using our everyday intuition. Our brains are hardwired for a different kind of reality. Our everyday experiences are limited to 3 spatial dimensions: up, down, left, right, forward, backward. We navigate through these dimensions. The balloon analogy helps, but it's limited because it's a 2D surface expanding. We have to imagine that surface as representing our 3D space. Trying to picture 3D space expanding without a 4D or higher external space to expand into is where our intuition breaks down. We want to see it from the outside. Some theories in physics suggest the universe may have more dimensions than the 3 spatial ones we perceive, plus time. String theory, for example, posits many more. If there are extra dimensions, the expansion might be happening within a higher dimensional space, but we are confined to our expanding 3D slice or brain. However, even without extra dimensions, the standard model describes the expansion as happening in all 3 spatial directions simultaneously. Every point is moving away from every other point. This expansion is not necessarily limited by any boundary. The universe doesn't have an edge that it's expanding away from or towards. The universe could potentially be infinite in extent. If it's infinite, it was always infinite, even at the Big Bang, and it's just becoming more infinite, with distances between points increasing. Or the universe could be finite, but without an edge, like the surface of a sphere, but in 3 dimensions. If you travel in one direction, you'd eventually come back to where you started, without ever hitting a wall. In either case, infinite or finite, but unbounded. There's no outside for the universe to expand into. The expansion is happening within its own structure. Visualizing this requires letting go of the idea of a container and embracing the idea that space itself is dynamic and growing. The implications of this cosmic expansion are absolutely far-reaching and fundamental to everything we understand about the universe. It's not just a theoretical curiosity. One of the most direct pieces of evidence for expansion is its effect on the wavelengths of light from distant galaxies. As the space between us and a distant galaxy expands, the light traveling across that space gets stretched. This stretching causes the wavelengths of the light to increase, shifting them towards the red end of the electromagnetic spectrum. This is what we call cosmological redshift. The more distant a galaxy is, the more space there is between us, the more that space has expanded since the light left the galaxy, and therefore, the greater the redshift we observe. This redshift distance relationship, first observed by Edwin Hubble, is the cornerstone evidence for the expanding universe. It shows galaxies aren't just moving, but the space between them is growing. The expansion also influences the overall density of the universe. As space expands, the matter and energy within it are spread out over a larger volume. This leads to a decrease in the average density of the universe over time. This has crucial implications for the universe's geometry and its ultimate fate. Similarly, the expansion influences the overall temperature of the universe. The cosmic microwave background radiation, the afterglow of the Big Bang, has been redshifted and cooled by the expansion over billions of years. Understanding the expansion rate and how it has changed over time is crucial to understanding the universe's past. By running the expansion backward, we arrive at the hot, dense state of the Big Bang. It's also crucial to understanding the universe's present state. The current rate of expansion and the discovery that it's accelerating tells us about the mysterious dark energy that dominates the cosmos. And perhaps most excitingly, understanding expansion is crucial to understanding the universe's future. Will it expand forever? Will it eventually collapse? The answer depends on the interplay of expansion, matter, and dark energy. Because of these profound implications, the expansion of the universe remains a central focus of cosmological research. Scientists are constantly refining measurements of the expansion rate and studying its history. So while the question, what is it expanding into, might seem simple, the answer is a testament to the truly mind-bending nature of the cosmos. It forces us to think beyond our everyday experience. It reflects the ongoing, incredible quest to unravel its deepest mysteries. It shows us that the universe is stranger and more wonderful than we could have possibly imagined. And that, I think, is pretty awesome. Thanks for joining me on this journey into the expanding universe.